Next, number 21, find the critical numbers for the following equation. In order to find the critical numbers, we need to take the derivative and set it equal to 0 and solve for x. So, to find y prime, given a rational function, we're going to need to use the quotient rule. We've got the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. And then we need to set that equal to 0 and solve for x. So replacing y prime with 0. Notice if I multiply both sides by the denominator, here instead of recopying all this, I'm just going to say d for denominator. If I multiply both sides by the denominator will cancel, and over here we still have 0. So really we're just concerned with where the numerator equal to 0. If I simplify the numerator, we're going to have 1 plus x squared minus 2x squared. Combining like terms is going to give us a negative x squared. And then if I move that to the other side, we're going to get x squared equals to 1. Taking the square root of both sides, we can see that our critical points are plus and minus 1. And that's it for this problem. Next, number 22. Find the x-coordinates of the inflection points for the following equation on the indicated interval. And so here, inflection points occur at the second derivative, so we're going to need to find y double prime. And in order to get there, we need to start with the first derivative. Here we have sine squared x, which is going to require the power rule. So the 2 comes down, the stuff inside stays the same, the stuff inside being the sine x. And then we minus 1 from the power would give us just sine x to the 1, or just sine x. And then multiplied by the derivative of the stuff inside, which would be sine x, the derivative of which is cosine x. There is our first derivative. And then to find the second derivative, we're going to need to use the product rule. So we've got the derivative of the first. The derivative of sine is cosine x times the second, plus the first times the derivative of the second. The derivative of cosine is negative sine x. And then we need to set that second derivative equal to 0 and solve for x. Simplifying is going to give us 2 cosine squared x minus 2 sine squared x. Next, I want to divide through by 2 just to simplify this equation some. Getting rid of those coefficients of 2. That's going to give us 0 equals cosine squared x minus sine squared x. And then in the next step, if you recognize what we have here, this is one of our trig identities. This is the formula for cosine of 2 theta. So I'm going to do a substitution, replacing with cosine of 2 theta. And then what we can do is we can say, well, can we just figure out what angles in the unit circle have an x-coordinate of 0? And that'll be what our 2 theta should equal. We know that in the unit circle, the angles that have an x-coordinate of 0 are pi over 2 and 3 pi over 2. Dividing through by 2, that's going to give us pi over 2 divided by 2, which is pi over 4. 3 pi over 2 divided by 2 is 3 pi over 4. And once we get these values of x, we need to check and make sure that they are both on the interval given. Pi over 4 and 3 pi over 4 are both between 0 and pi, and so these are both values of x where we will have an inflection point. Next, number 23, determine the intervals for which the equation is concave down. That means we're going to need to find the second derivative and then find out where the second derivative is negative. Starting with the first derivative, that's going to be 6x squared minus 2x. The derivative of the constant goes to 0. Taking the second derivative is going to give us 12x minus 2. And then what we need to do is we need to know when is this negative. So next, we need to find the critical point. Setting this equal to 0, solving for x, we're going to have 12x equals to 2 divided by 12 and reduced is going to give us 1/6. And then on a number line, knowing that this is our only inflection point, we need test points. So less than 1/6, 0. Greater than 1/6 is 1. We're going to plug those test points into our second derivative to see whether we get a negative or a positive value. Plugging in 0, we get -2, which is negative. Plugging in 1, we get 10, which is positive. And this section of the number line indicates where we're going to be concave down. So we would say that this graph is concave down from -infinity up to 1/6, and that's going to do it for this problem. Next, number 24, we need to evaluate this definite integral. Now it says use substitutions may help, but in this case I can see that I have just a simple polynomial expression, so we're going to find the antiderivative of each term separately. The antiderivative of 2x is x squared. We know that because when you do the power rule backwards, you have to add 1 first to the exponent, giving us a squared, and then you divide the coefficient by the new exponent. 2 over 2 is 1. So that's how we get the antiderivative of the first term. And then for the next term, that's going to be negative. Adding 1 to 2 gives us x cubed. Dividing the coefficient by the new exponent gives us just a 1. And then this antiderivative needs to be evaluated from 1/2 to 1/3. So that's going to give us 1/2 squared minus 1/2 cubed. That is this expression evaluated at 1/2, and then we minus the same expression evaluated at 1/3. That'll be 1/3 squared minus 1/3 cubed. And then to work that out, you can either do it manually or electronically. I'll show the steps. 1/2 squared is a 1/4. 1/2 cubed is an 1/8. Minus 1/3 squared is a 9th. 1/3 cubed is 1/27. And then I'm going to pull up my class whiz for help. So we've got 1/4 minus 1/8, which is 1/8, minus 1/9 minus 1/27 is 2/27. And then subtracting these values, we have 1/8 minus 2/27, giving us a final answer of 11 over 216. And that is the answer for question 24. Next, 25, another definite integral, starting with the antiderivative of e to the x, which is e to the x, minus the antiderivative of 1 over x. And if you think backward, what would I take the derivative of to get 1 over x? That is natural log of x. So the antiderivative of 1 over x is natural log of x. There's my antiderivative. this expression needs to be evaluated from 2 to 1. So we're going to get e squared minus natural log of 2. That is this expression evaluated at 2. And then we're going to subtract the same expression evaluated at 1. E to the 1 is just e minus natural log of 1. And then if I simplify, e squared minus natural log of 2 are going to stay the same in order to keep the answer exact, minus e, and then we know that the natural log of 1 is 0. So that just goes to 0, and then this would be our answer if you want the exact value. Otherwise, you would need to put that into the calculator if they ask for an approximate value. And one quick note, you could also express this in this form. If you want to rearrange the terms, that's fine. Both of these answers are numerically equivalent, and so both would be given full credit. Next, number 26, we have another definite integral. What I want to do first is I want to rewrite this integral in a different format. Notice that the numerator is 6. What I can do is I can pull that to the front as the coefficient of 1 over the square root of 1 minus x squared. And then since this is now a coefficient of this fraction, what I can do is I can actually pull that in front of the integral. So that's going to give me 6 times the integral from 0 to a half. And then this you should recognize as one of our derivatives. It is the derivative of inverse sine of x. And so what I can do, doing the antiderivative, would give me the inverse sine of x. So let's rewrite like this. This is 1 over square root of 1 minus x squared with respect to x. Forgot my dx there. And then we know that the antiderivative of this fraction is inverse sine of x. And that needs to be evaluated from 0 to a half. So we're going to have 6 times the inverse sine of a half minus the inverse sine of 0. So what is the inverse sine of a half? Well, that basically says where is y a half in the unit circle? Somewhere from negative pi over 2 to pi over 2, that's going to produce an angle of pi over 6. And then the inverse sine of 0 is 0. That's where y is 0. Add an angle of 0. And then this is going to simplify nicely. The 0 disappears. The 6 is reduced. Our answer is pi. And that's going to do it for problem 26. Next, 27, we have another definite integral. And this time I am noticing that I've got the square root of 1 minus x squared, and that is multiplied by x. So this is one of those cases where it's probably going to be to our advantage to use a u substitution. Let's say let u equal the radicand. 1 minus x squared, the stuff under the radical, and then I immediately differentiate both sides, giving me du equals the derivative of 1 minus x squared is minus 2x times dx, dividing both sides by negative 2x, is going to tell me what I can replace dx with. So, simplifying, that's going to give us the integral from 0 to 1. The x is still here, but 1 minus x squared is u. So we're going to replace that with u, and then we're going to replace dx with what it's equal to, which is du over negative 2x. And now we can see that this substitution is going to work well, because these x's will reduce out. leaving me an expression completely in terms of u. So we're going to have the integral from 0 to 1. Don't forget about this negative 2 in the denominator. That's the same as 1 over negative 2 times the square root of u du. And then since this is a coefficient, we can bring him to the front, giving us negative 1/2 the integral from 0 to 1. And now I'm going to rewrite the radical symbol as a rational power. That's going to make it easier to integrate. So taking the antiderivative, that's going to give us negative 1/2. If I add 1 to the power, that'll give us u to the 3/2. And then I need to divide by the new exponent, which is the same as multiplying by the reciprocal. That is our antiderivative, which we can then replace u with what it's equal to, which is 1 minus x squared. Okay, so then this is going to equal, here these 2's reduce out, giving us negative 1/3, 1 minus x squared, to the 3/2. And then remember, this needs to be evaluated from 1 to 0. Okay, so plugging in 1 first, we're going to have negative 1/3 times 1 minus 1 squared, all of that to the 3/2 power, and then minus a negative will make that a positive 1/3, 1 minus 0 squared to the 3/2 power, which will simplify. 1 minus 1, this becomes 0. And 0 to any power is still 0, and 0 times anything is 0. That's just 0. Plus 1 minus 0 is 1. 1 to any power is 1, and then 1 times 1/3 is 1/3, giving us a final answer of 1/3. Next, number 28, we have another definite integral. And this time, this fraction looks like something we've seen before. In fact, it is the derivative of the inverse tangent of x. So we know the antiderivative of 1 over 1 plus x squared will be the inverse tangent of x. So what we're going to have the inverse tangent of x evaluated from square root of 3 to 0. So that's going to give us the inverse tangent of the square root of 3 minus the inverse tangent of 0. And the inverse tangent of square root of 3, pi over 3. Minus the inverse tangent of 0 is 0. And that's going to give us a final answer of pi over 3. And that's going to do it for this particular problem. Next, number 29. Here we have another definite integral where we have 3x times e to the x squared. Notice the difference in degree of the exponent of the e and the coefficient here is a difference of degree 1. And that is a good indication that we want to do a u substitution. So we're going to say let u equal the higher degree of x. We're going to let u equal x squared. And then if we differentiate both sides, we're going to get du equals 2x dx. Dividing both sides by 2x is going to give us the expression that we can substitute for dx. Now, rewriting the integral. From 0 to 2, this 3x is still here. But now this becomes e to the u because we let x squared be u. And dx is going to get replaced with du over 2x. And then here we can see that this is going to work nicely because we have an x top and bottom, and those x's will reduce out. Now, we do have a 3 over 2, so that's going to give us the integral from 0 to 2 of 3 halves as the coefficient of e to the u du, and then that 3 halves can be pulled out to the front. Next, simplifying this integral, I'm going to pull out the 3 halves. I'm going to take the antiderivative of e to the u, which is e to the u, and then I'm immediately going to replace u with what it's equal to. Remember, we let u be x squared. So that's going to be 3 halves e to the x squared evaluated from 2 to 0. And that's going to give us 3 halves e to the 2 squared minus 3 halves e to the 0 squared. Simplifying is going to give us 3 halves e to the 4th minus 3 halves. Now this right here, 0 squared is 0, and e to the 0 is 1. So 1 times 3 halves is just 3 halves. This answer would be fine. If you want to factor out the 3 halves, you can, but it's not required. And that would give us 3 halves e to the 4th minus 1. Either one of these answers would be sufficient. Next, number 30, they want us to find the area under the curve. That indicates a definite integral for this equation on the given interval from 0 to pi over 3. So we're going to rewrite this as a definite integral from 0 to pi over 3. We want the antiderivative of secant squared x tangent squared x with respect to x. And this one is a little tricky as far as picking the appropriate u substitution to make this a lot easier to find the antiderivative of. What we want to think is, what would you take the derivative of to get secant squared x? And that is tangent. So we're going to say let u equal tangent x. And then if I differentiate both sides, the derivative of tangent is secant squared x dx, dividing both sides by secant squared x is going to tell us what we need to replace dx with. Now, notice that we did say to let u be just tangent of x. Over here we have tangent squared x. So if I do my u substitution, that's going to become simply u squared. So here we go, rewriting this integral from 0 to pi over 3. We're going to have our secant squared x times u squared, and then dx gets replaced with du over secant squared x. Notice that that will eliminate the secant squared x's, giving me an integral in terms of u only. Now, rewriting the integral from 0 to pi over 3, this is simply u squared du. The antiderivative of u squared, if we add 1, gives us a u cubed, and then divide the coefficient by the new exponent, giving us a third. And then we can replace u with what it's equal to. And u was just tangent x. So this is going to be tangent cubed x, and then evaluated from 0 to pi over 3. That's going to give us 1/3 tangent of pi over 3. I'm going to write it like this: quantity cubed minus 1/3 tangent of 0 quantity cubed. And then we can simplify this expression using the Casio. What I want to know is, what is tangent of pi over 3 cubed? Well, tangent of pi over 3 is square root of 3, and then that answer cubed gives me 3 square root of 3. So that's going to be 1/3 times 3 square root of 3 minus, and then I believe the tangent of 0 is 0, which makes this entire term go to 0, so I don't really have anything to subtract. That's just 1/3 3 square root of 3. Oh, and then these 3's cancel. Look at that. How nice that simplifies to just square root of 3. Next, 31. The acceleration of a function and the initial velocity are given for a particle moving along a line. Find the velocity at time t and the distance traveled during the given interval. So if I have the acceleration equation, we know that the antiderivative will give us the velocity. So capital A of t, remember we use a capital letter to represent an antiderivative, that will equal our velocity function, and we need to do the antiderivative of t plus 4. So for the t term, we're going to add 1 to the power, and then divide the coefficient by the new exponent, 1/2 t squared, plus the constant just gets a t, and then we need a plus c, because this is a general antiderivative. We need to allow for any constant that may have been there. And now we're going to find out what that constant is based on this given initial condition. We know that when t is 0, the velocity is 6. So now the velocity is 6 whenever t is 0. So 1/2 0 squared plus 4 times 0 plus c. These both go to 0, telling me that c is 6. And then we can come back to here and say that our velocity equation at time t, that means the general velocity equation, is 1/2 t squared plus 4t plus 6. That is the answer to the first part of the question. And then to find the distance traveled, we need the antiderivative of velocity. So capital V, the antiderivative of velocity, will give me the distance or position equation, call it s of t, and then we need to do an antiderivative again. So adding 1 to the first exponent gives me t to the third, and then if I divide 1/2 by 3, I get a 1/6, plus adding 1 to the next exponent. 1 plus 1 is 2. Dividing 4 by 2 gives me a 2. The 6 is going to get a t, and we don't need the plus t since this time we're doing a definite integral from 0 to 10. So the distance traveled would be the integral from 0 to 10 of the velocity equation with respect to t, which we now have the antiderivative, would be 1/6 t cubed plus 2t squared plus 6t, all of that evaluated from 0 to 10. Now, the nice thing about doing this evaluation is when I plug in the 0, since everybody has a t, that is just going to go to 0. So really all I need to calculate is this expression evaluated at 10. So that's going to give us 1/6 times 10 cubed plus 2 times 10 squared plus 6 times 10. And then if we evaluate that using our Casio, we're going to get 1280 over 3, which is approximately 426.7 rounded. So if they want the exact answer, that would be 1280 over 3, or approximately 426.7, whatever the instructions ask for. And if I go back to our instructions, it doesn't specify. And if it doesn't specify, usually they want the exact value. Notice that our distance was measured in meters. So if we want to include the appropriate units, we would say meters or meters. And that's going to do it for that problem. Next, number 32, the rate in gallons per hour at which oil leaks out of an oil tanker truck that crashed is represented by the function. And so here we have the function that represents the rate at which we're losing oil. How much oil leaks out in the second and the fourth hours of the leak? So the second hour would be represented by from the end of the first to the second. In other words, if you're finding how much oil leaked out given the rate, that's going to be the integral from A to B of the rate with respect to t. So in the second hour, that's going to be from 1 to 2. Does that make sense? From 0 to 1 would have been how much oil we lose in the first hour. And then from 1 to 2 would be how much oil we lose in the second hour. So we're going to want to do this integral, and we're also going to want to do the integral from 3 to 4. That's going to take care of the fourth hour. And so we need to set up these integrals separately and evaluate. So here I've got my first integral set up. We need to find the antiderivative starting with the 1000. That constant simply gets a t, and then the antiderivative of 60t. We're going to add 1 to the power, giving us t squared. 60 divided by 2 gives us a 30. And then we need to evaluate this from 2 to 1. Plugging in the 2 first is going to give us 1000 times 2 minus 30 times 2 squared. Okay, that minus 1000 times 1 minus 30 times 1 squared. And giving us 2000 minus 2 squared is 4. 4 times 30 is 120 minus, this is 1000 minus 30. And then I would recommend that you do the calculator from here on out. We're going to have 2000 minus 120 minus parentheses 1000 minus 30. And our final answer is 910. 910 what? Gallons of oil. And then we need to repeat the process for the second part of the problem, the integral from 3 to 4. Now this is going to be exactly the same as the previous problem except for our boundaries. Going from 3 to 4, we still have the same antiderivative. Now we're going to evaluate at 4 first. That's going to give us 1000 times 4 minus 30 times 4 squared minus 1000 times 3 minus 30 times 3 squared. And then if you want to put all that in the calculator at one time, you can, or you can do it in a couple of steps. So just showing a couple of steps here. 4 times 1000 is 4000. 4 squared is 16. 16 times 30 is 480 minus, this is going to be 3000 minus, 3 squared is 9. 9 times 30 is 270. And I think then I'll grab the calculator. 4000 minus 480 minus parentheses 3,000 minus 270 gives us an answer of 790. 790 what? Gallons of oil that we lose in the 4th hour. And the last problem on the practice final exam for Cal 1. It says find the maximum vertical distance between this curve and this curve on the interval from 0 to 2 pi. And so the first thing I'm going to do over here on the graph they've given me is I'm going to mark off from 0 to 2 pi. That means I could ignore all of this graph over here and then anything that shows up over here. I'm only looking for the maximum vertical distance within these range of values. Now, if you think about it, what we're really asking for is, if I look at just a couple of points here, making sure that this is going to be vertical, we're looking at the difference from this y value to this y. Okay, so let's simplify it. We're looking for y2 minus y1. That is the vertical distance between the two graphs. We need to identify which of these equations represents the top graph and which one is the bottom. Okay, so how do we do that? Well, notice that these graphs have a different y-intercept. So if I plug in a 0 for the second equation, the cosine of 0 is 1. 1 plus 1 is 2. And that gives us a point on the top graph. So then what I'm going to do is I'm going to put a box around this guy and say that he's the one on top. And then that makes this one the one on bottom, which in my equation now, this is y2, and this one is y1, because you want to subtract the larger y from the smaller y. Okay, so we can rewrite this expression then, and we can say that the distance between the two graphs, the vertical distance, is y2, which is 1 plus cosine of x, minus y1, which is negative 1 plus sine of x. So this is our equation that represents the distance between the graphs, the vertical distance, for any value of x. And then let's simplify that and write it in function notation, okay? So the difference with respect to x, negative and a negative make a positive. See, I'm going to need to distribute this negative. 1 plus 1 is 2 plus cosine x, and then distribute the negative makes that a minus sine of x. And then how do we find a maximum or a minimum? Well, we find critical points. So we need to differentiate this function, set it equal to 0 and solve for x, and then look for any solutions that are on this interval from 0 to 2 pi. Here we go. The derivative of our distance equation. The derivative of a constant goes to 0. The derivative of cosine is negative sine x, and the derivative of sine is cosine. And since that already has a minus in front, it's just going to be minus cosine x. So there's our derivative, and then we need to set that equal to 0 and solve. So 0 equals, if I factor out the negative, that's going to give me sine x plus cosine x. And then if I divide both sides by negative 1, I can just eliminate the negative sign. Okay? So then the next step that I'm going to do is I'm going to move one of these trig functions to the other side. Let's move cosine over, okay? So then the sine of x will be positive. It's going to equal to negative cosine x. And then the next step I'm going to do may seem a little weird, but it's going to make sense to me. I'm going to divide by cosine x, okay? So why do I do that? Well, for one thing, it gets rid of this trig function on the right-hand side, and makes that effectively -1. On the other side, this will simplify to a single trig function. I know that sine over cosine is tangent. So now what I'm really trying to solve is, when is tangent of x equal to -1? Well, on the interval from 0 to 2 pi, the angles for tangent that produce -1 are 3 pi over 4 and 7 pi over 4. So these are my two candidates for where the maximum might occur at. And then if you remember, we also need to check the endpoints to make sure that the endpoints don't actually contain the maximum value. So let's do this. Let's erase this. Let's make a note that our critical points are 3 pi over 4 and 7 pi over 4. And then what we want to do is we want to set up a table that will allow us to compare all of the values of x where the maximum might occur. So here we're going to have x and our distance equation. So we need to check the endpoints, which are 0 and 2 pi, but we also need to check our critical points, 3 pi over 4 and 7 pi over 4. And then what we want to do is we want to evaluate our distance function, the original distance equation that we wrote, which was, again, d of x equals 2 plus cosine x minus sine of x. We need to evaluate this equation at these values of x to see which produces the largest value. Okay, so on my Casio, evaluating the first value of x, the first endpoint, make sure you're in radian mode, by the way. That's going to give us a distance of 3. So if I go up to my graph, what that tells me is that the distance between the y-intercepts is a distance of 3. And that's pretty easy to see because we're going from -1 up to 2. That is the distance for that value. And then with the Casio, you can simply scroll back through and delete the 0 and input your next value that you want to check. So 3 pi over 4, we're going to check that first critical point, and that's going to give us, on the Casio, 2 minus square root of 2. I would really like to have that as a decimal, so I'm going to hit the SD button, and that is 0.59 rounded. 0.59. I think what that's going to end up being at 3 pi over 4, which is, let's see, if this is pi, that would be a half, and this would be a fourth. You know what that's going to represent? That's our minimum. That's where the minimum distance occurs. Let's keep checking. Again, scrolling back through, now we're going to change our 3 pi over 4 to 7 pi over 4. And that's going to give us 2 plus square root of 2, which is approximately 3.41 rounded. And notice that that value is bigger than 3. So that means that 0 cannot be the maximum. Remember, we think this is the minimum. It seems to be the smallest so far. And then we need to check our last endpoint to see if that is bigger than 3.41. And the value we get at this endpoint is 3, which is not bigger. But that also shouldn't be any surprise since the period for these waves is 2 pi. We're going to get the same distance at 2 pi as we have at 0. Again, that shouldn't have been a surprise that coincided with the same distance at 0. And so the final answer for this problem, the maximum distance occurs when x is 7 pi over 4, but they ask for find the maximum vertical distance. They actually wanted us to find the actual distance, and that's going to be this value here. So the answer that you would give for this problem is 3.41. That is going to be our maximum vertical distance between the two graphs. And that's going to do it for the end of the review for Calculus 1 final exam. So if you have any questions or comments, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.